Hi, welcome to our fifth lecture. So we are just about done with chapter 6. There's a little bit more material I want to do on chapter 6 right now. And of course, at the end of the semester, I'd like to come back and hit it, say, for half a lecture and extend what we've learned in chapter 6. But for today, what we're going to do is get started on chapter 7 first. And chapter 7 is about how to simplify analyzing flow. So to get an idea of what I mean by that, why don't we just take a look at this situation right here where we have some sort of flow and it's approaching some sort of object. We want to be able to say, hey, what's going to happen in this case? Well, the first thing you do is start gathering information about the scenario. So you would want to know fluid speed, fluid density, fluid temperature, fluid viscosity, fluid bulk modulus. You might want to know the roughness of the surface that it's approaching. Either maybe it's going inside the surface or the exterior. You might want to know the speed of sound in the fluid, and you might want to know lengths or dimensions related to this fluid, and then you would get going. Well, that is a lot of information to incorporate into some sort of analysis. And question that we want to get at is, hey, is there a way to simplify it? Indeed, there is, and there's some ingenious things that people have figured out to a way to take all this stuff right here, or not all of it, a portion of it, at least in the minimum, and combine them to get a parameter that'll tell us about the flow. So a bit about the first parameter. It applies actually to internal flow and external flow. So here's a case where we have a fluid approaching some sort of duct or pipe, and it's going to go inside. So our first question would be able to say qualitatively say, hey, what's going to happen in that case? What's it going to look like? And we have two main cases. I mean, they both come from the fact of thinking about, look, there's this no slip layer on the exterior, okay? And in one case, we end up getting what's called laminar flow. And laminar, you should think layered when you hear the term laminar flow. Okay, and that would be the idea that we have just layers of fluid flowing along parallel to the axis of our pipe, just sliding past each other. And that would be laminar flow. In the other case, actually, maybe this flow here is so fast and this pipe is so rough that eta is large enough that we end up getting some sort of swirling flow going on, where any layer of fluid doesn't actually maintain its motion and instead oscillates about. And oscillation is too strong a word. There'd be a randomness to this. And that's called turbulent flow. And it turns out with this particular scenario, which is of course huge in engineering, where you have a pipe flow going through a pipe, that's one of your first decisions as your analysis decides laminar turbulence. So you look up all this information here and try to put it together along with maybe the pipe diameter and some other information. And how are you going to decide on laminar turbulence? Once again, it comes down to combining some of this information into a single parameter. All right, the next case we want to take a look at a little bit is what if we had external flow? Well, what could happen in this case qualitatively? And once again, we have the same thing. We have the same dichotomy. Maybe the flow will be laminar, where this stream here will go smoothly over and maybe split and go really smoothly over and recombine. And these will actually do the same thing and smoothly go over and come back to their original position relative to that middle one at the end. Now, my drawing's not great, but if you had some time, you could imagine, hey, this goes over and then just comes out parallel, and this goes up, down and comes out the same parallel to this one right here. And the spacing at the end is equal to the spacing at the beginning. Well, that's laminar flow. Alternatively, we could have some sort of situation where this speed is so great or this surface is so rough, so we end up getting swirling flow at somewhere along here where the fluid does not actually follow a streamline and is swirling in nature. So again, how are we going to decide on that? Well, we're going to take some information like the roughness of this plane wing, the speed of the fluid, the length of the plane wing, what this span is, and also the density of the fluid, viscosity of the fluid, speed of sound in the fluid, etc. So how are we going to go about deciding, putting that together? Well, this is the most famous case of there being a single parameter which combines those that information, and that parameter is called the Reynolds number. So that's what we're going to start with as far as our simplifying parameters. There are several, but the most important one in fluids is the Reynolds number. And it's pretty amazing that if you calculate the Reynolds number, it will tell you whether this is laminar or turbulent. And furthermore, it will tell you a lot about the shape of the flow. So if we get the Reynolds number is equal to 5,000 for a fluid, we're going to have either laminar or turbulent, and we're going to have a certain behavior of this flow. And that's going to be true no matter what the fluid is. If the fluid is air, if the fluid is water, if the fluid's engine oil, and its Reynolds number is 500, in an important sense, it's all going to behave the same. And we'll have the same thing over here. So what is this dimensionless parameter of the Reynolds number? Well, I would hope that it's probably a good idea for you to take out those tables that we've been using. There are those 5 basic tables that are at the beginning of the book, and we'll get going on looking at those terms for relevant terms for different fluids and working out the Reynolds. Again, the first parameter is called the Reynolds number, and it's abbreviated as RE. And what we're going to do for a flow when we calculate the Reynolds number is we're basically trying to say how likely is it are we going to get turbulence. The larger the Reynolds number, the more likely we're going to get turbulence. So before we get going on how that calculation is normally done, 2 things. I'd like you to be aware that in Chapter 7, many of the parameters are listed. There's got a good long list of different parameters, and as you look your way down 7.1, there's lots of different parameters which end up combining some of those factors that we think about when characterizing the flow. So density, temperature, viscosity, speed of sound in the fluid, etc. And each one tells us something. Probably the number, no, not probably, definitely the number one out there is the Reynolds number. So we want to come out of ME120 being really solid on that. So first of all, a little bit of intuition. No need to copy this down. We're going to instead do pipe flow. But this picture right here would be is supposed to represent a case where we have, say, a fluid flowing in a pipe, and then at some point that pipe ends up widening. So we essentially have a diffuser, and maybe after that it continues on in a larger pipe section. So in some cases like that, you actually get turbulence. This fluid, as it spreads out, develops a bit of a swirling flow. All right, in general, no matter what the geometry, we're going to combine a fluid and its flow with some sort of geometry, some sort of object, internal or external. This is internal. We're going to think about, hey, what might cause separation versus what would oppose separation. If you have 2 layers of fluid, laminar flow, 2 layers of fluid, and if they suddenly separate, okay, you can get a low pressure in here where fluid will deviate and start to swirl. So if we're thinking about turbulence, we're going to think, what's the likelihood of separation? All right. If you just think about a car or something like that, or a plane, the likelihood of turbulence, probably the first thing that's going to come to your mind is fluid speed. Absolutely, fluid speed is going to be in there. And if you're thinking, okay, well, what's the likelihood that flow will not separate? It's going to be cohesion, so it's going to be velocity. So definitely we're going to have fluid speed always on this list for what might cause separation, and we're going to have fluid viscosity on there for what is going to prevent cohesion, probably prevent separation. But what else are we going to have in there? So let's just take a look at this case right here, and I'm going to simplify it a little bit where I'm just going to try to get rid of this other little bit of pipe that I drew in this top section right here. So we're just imagining, just taking a look at the bottom portion of the fluid, all right? So we got the bottom of the fluid, this fluid is going along, and then the pipe wall or the wall actually deviates. Okay, well, what might make it likely that actually we end up getting separation in that case? And part of it would just have to do with this angle right here like this. The sharper this angle, the more that the fluid here, this fluid here, has to turn, and the more in order to hug this wall. And then this fluid is going to follow Newton's first law. A fluid tends to go in a straight line motion, and we could get separation in this case, and then we'll get that swirling. So another factor in there would be something to do with theta, how big the turn is. All right, so every geometry out there, there's some sort of intuition that, hey, what about this geometry makes it more likely that we're going to get separation? And from that comes some parameters that we combine together in a single number and calculate and determine whether there's going to be the likelihood of turbulence. So pipe flow, give me just a second to draw a pipe, okay? And we'll try to think about what factors might end up leading to turbulence. Okay, so I got a pipe that I've drawn here. I'll get it up there for just a second, and I've got its diameter, and I have a fluid to go in through there. And let's say that it has some sort of average speed that it enters in there. So there's my picture. There's a pipe. It's got some sort of diameter. And it's got some sort of average speed going on there. Okay, well, what about the likelihood of that we end up getting separation in a case like this? Well, one easy way to think about it, it's really going to depend on how many kilograms per second we try to put through there. There's only so much space that the fluid can actually flow in there. And if we try to pack more and more stuff in there, it's going to be harder for it to fit. We also want to keep in mind that there's this no slip condition at the wall. So there's a bit of fluid here that's not slipping, a bit of fluid here that's not slipping. When this fluid comes in, we have this fluid coming in and entering. The stuff out at the extremes actually has to deviate and go up a little bit because of this no slip condition. So without a lot of precision, we can say, look, m dot is going to make a big difference. Okay, so we got that. That's going to make a difference. Okay, but what if we have a certain mass flow, like we're trying to put 40 pounds per minute through this pipe? What difference is it going to make as the diameter is bigger and bigger and bigger? So we could imagine putting it through a small pipe or a larger pipe. Okay, well, the larger the pipe is, the greater the area that fluid can fit through, and the less this effect due to the no slip condition that causes deviation around the edge. So the bigger the diameter is, the less likely we're going to get separation, the less separation forces we have. So many times in fluids, we say, we have this factor m dot over d that tells us a combination of the fluid flow and the geometry, what likelihood there's going to be separation. Okay, if we do have some separation that might be occurring, there's a tendency for flow lines to deviate a little bit. What prevents that? Well, that's always viscosity. Viscosity is like cohesion, and so we have that term there like that. Okay, so life would have been a little bit easier if we said, hey, that's good enough. When we figure out whether we're going to get if we're trying to assess the likelihood of turbulence in a pipe, we're going to calculate m dot over d for this scenario, and for the fluids, we're going to get the viscosity, and we're just going to try to combine those numbers. We would be done. But there are two more things to do. Usually what we do is we do a ratio, separation over cohesion. If separation over cohesion is large, separation wins, we get turbulence. If separation over cohesion is small, cohesion must be large, and we don't get turbulence, we get laminar. So basically what we're going to do is we're going to do m dot over d all over the viscosity, okay? And that is a pretty good calculation that you're welcome to do, but it turns out a little bit of manipulation is done. First of all, we don't like fractions within fractions. So you can think about the calculation we're going to do is m dot d over mu. Secondly, every single Reynolds number we like to express in terms of the average speed of the fluid. Okay, the average speed of the fluid. So how could we get from m dot to average speed? And that's not that hard to do. Hopefully you remember that m dot is rho v cross-sectional area. So m dot is rho VA. So I'm going to put that there. Density, speed, and then how about the cross-sectional area of a pipe? By the way, I'm sorry, I have a mistake here. You guys probably caught that. I should have probably had the diameter in the bottom. Okay, the cross-sectional area is pi d squared over 4. Okay, so now I have m dot, and on the bottom, I have the density times the viscosity. Okay, and there is a calculation that takes into account the ratio of the separation forces and divided by the viscosity. Well, then it's actually simplified a little bit if we want to do that comparison. You see that we have a d squared here and a d there, so those could go away. And we're still going to have the viscosity. So we could simplify it as rho v d over mu. Certainly there's a pi in there and a 4, but those are constants. And if we're just trying to do a comparison, we don't need them. And so there is our formula for the Reynolds number. In some textbooks, they do D saying, hey, this Reynolds number applies to pipe flow, which has a diameter. There will also be Reynolds number where this is an L, and it might stand for, say, like the length of a wing or something like that. Okay, so for pipe flow, if we're assessing the chance that there's going to be turbulence, we are going to think a little bit about mass flow and diameter and viscosity and visualize what's going on. but pretty quickly we're just going to go in and calculate that parameter. All right, so basic relationship for Reynolds number for a very particular situation. Subscript E, this is for pipe flow. In general, any situation we have, so if we have wind approaching a building and going around a building, we're going to get a Reynolds number for that to help us evaluate whether there's turbulence. And in general, the parameters we're going to use are density, speed, fluid viscosity, and then we're going to have some sort of length associated with the geometry, some sort of distance associated with the geometry. For our particular case, it is the pipe diameter. So get rid of that building. We're not doing buildings. We'll take a look at external flows in chapter 9. Right now we're doing internal flows. So hey, anytime we have a new thing like mass times acceleration, way back when you were doing your basic physics, we'd like to give it a unit. So let's go through and see how these units turn out. All right. So I think it's easiest to get it at, or might be easy to get it at SI. So without worrying about numbers, let's go ahead and get the units up there. And you try it yourself. Go ahead and pause the video and see how does this whole thing crank out unit-wise, rho v d over mu. All right, I'm going to get going. All right, so there it is. That's a mouthful. We definitely want to see if we can simplify it and hopefully remember that with a lot of stuff related to viscosity, if we can find a Newton or if we can find a pound in there, that'll work out well. So let's see if we can go ahead and find a Newton somewhere in the denominator. Recalling that a Newton is a kilogram meter per second squared. So I'm looking for a kilogram meter per second squared somehow. Got that kilogram. There's 1 meter, I can use that there. And I've got a second there and a second there. So these 4 together combine to give a kilogram meter per second squared. So I'm just going to go ahead and separate those out, kilogram meter per second squared, and see what I have left. Okay, in the numerator, I still have this meter and that meter cubed. So I'm going to be a little bit slow and just write that down. Okay, and then how about the denominator? I've got this Newton here, and in addition, I took that second and combined it with that second to get second squared. So I've taken care of this second, but I'm left with that meter squared, so I've got 1 over meter squared. Okay, that still is a mouthful. We'd like to be simpler than that, and what we did, the reason we separated this out because that was a Newton, okay? And hopefully you can stare at that for just a second and see what we have left. And if you're thinking, hey, all the units cancel out, you are exactly right. This is a unitless parameter, the Reynolds number. It's a unitless parameter. So when you're thinking about the Reynolds number and you're maybe like writing this equation down on your equation sheet, it is unitless. Okay, so it is a unitless parameter. That's going to be true in British units or English units. So you might want to confirm that yourself. I'm just going to go with it. So we know, though, that this turns out to be unitless. The thing to do then is to do some practice with different fluids and scenarios and see how this Reynolds number turns out. And you eventually get to the point where you get pretty comfortable with it. So let's start with an example where we have a 3-inch tube and we have air going 2 feet per second. 3-inch tube is becoming pretty common for those of you who have done some duct work. Usually ducts are bigger than 3 inches, but there's some systems out there which distribute ventilation air to homes and buildings using these small 3-inch tubes that wind through. They're pretty easy to fit, and they're pretty effective. Hey, to what degree is that going to be turbulence? Well, you're going to calculate the Reynolds number. So I would be doing the speed, the density of that fluid times its average speed. Remember, it's going to slow down a bit near the edges of the tube because of the no-slip condition, and it's going to speed up in the middle, but we're saying on average it's going 2 feet per second. Diameter ends up being in the numerator, and then viscosity ends up being in the denominator. So hopefully you're pulling out that table that's at the beginning of the book and looking up the data, and I'm going to get it up there, and we'll crank through it and see how it all turns out. So density of air, by the way, for all these examples we're going to assume it's the standard temperatures that allows us to use 1.5, 1.6, 1.7, or 1.8. So air has very, very low density, 2.38 times 10 to the negative third. Okay, the speed is 2 feet per second. I am being a little bit lazy because I'm not putting in units, but I encourage you to try it once and test it yourself. These units, this whole calculation is going to end up being unitless if you fill in with the units that are in table 1.7 in this case. All right. How about the diameter? That would be 3 inches, but we want to be consistent. This, for example, is slug per feet cubed. So we would want this to be in feet as well. So I'm going to do 0.25 feet. All right. And then how about the viscosity of air? How viscous is it? How its tendency to stick together? And you should have a very, very low number. And my table is giving, wow, 3.74 times 10 to the negative 7th. All right, and then take your time, calculate it once or twice, and see if you match what I end up getting. So the answer is supposed to be 3,182. It is unitless. It's a pretty big number in a sense. We haven't done very much yet, but hey, 3,000 is a pretty big number, and that's in part because this viscosity is so low. Couple other things, comments about it. What does that actually mean? We're not there yet. We just have this number, okay? But if you read in the textbook is going to say that this Reynolds number tells us a ratio of, well, this is cohesion, and this is separation forces, or they sometimes call it an inertial forces. So this would tell us that the inertial forces are 3,182 times as strong as the separation forces. Good enough for now. I think the thing to do instead now is to go to a different fluid and see how it turns out. So let's go ahead and take a look at, what if we did SAE30 oil? I'm just going to write it as oil, all right? And how is that going to turn out? Well, I feel better than better than the inertial versus the viscous is try to keep in mind, look, what we're doing is basically what makes this tough for a fluid to stay laminar is how much we're fitting in there. So now we have oil at 2 feet per second, okay? But oil is much more dense, okay? Oil is much more dense. So the amount of oil, the number of particles that will go through a certain surface area is going to be higher. So we're trying to fit a lot more mass in that area, okay? On the other hand, oil is a lot more viscous. So because of mass, I'm thinking it's more likely that this is going to be turbulent, but because of viscosity, I think it's less likely. So it's a tough call. How is it going to turn out? We got to crank the numbers. So once again, for oil, you're going to do rho v d over viscosity. Why don't you get the numbers up there, and I will do as well, and see how our answer compares to 3182. All right, so my calculations turned out to be 111. And looking at some of the details, oil is a lot denser than air. So we're going to be trying to fit a lot more particles through this pipe. If we're trying to have oil at 2 feet per second go through this through this entrance, there's a ton more particles of oil per that entrance area, a lot more going through there. So we're trying to squeeze a lot. That makes it more likely to be turbulent. On the other hand, oil is so much more viscous than water, and what wins out, than air. And so what wins out is we have a lower Reynolds number. So oil is much, much less likely in this case to be turbulent. And of course, that's one thing that we want with engine oil. We want engine oil to lubricate, and also to be something that promotes smooth smooth flow and smooth passages. So oil has those properties. All right, probably one more that's worth doing is water. How's water going to turn out? More or less likely to be turbulent? Well, water and oil's density are pretty similar, but on the other hand, water is less viscous than the oil. It is so much easier to pour water. So the cohesion forces that keep water molecules from separating, getting a low pressure, or water layers from separating and getting a low pressure area that leads actually to turbulence. those viscous forces are not very strong, we're probably going to get something more than 111. I don't know what your intuition is, but when I think of air, I think of incredibly low viscosity. So I'm guessing, my uninformed opinion would be that water is going to be somewhere between these two numbers. But let's crank the numbers and see how it turns out. Reynolds number for water in this scenario. Yeah, comparing water to oil, it looks like water won. It has, in a sense, it has a higher Reynolds number. So what's going on? 1.94 slugs per foot cube compared to 1.77. We are, if we're doing water compared to oil, we're trying to fit a lot more lot more particles through there. And that leads to more squeezing, more likely that you're gonna have turbulence. Okay, how about viscosity? Much lower viscosity. And so it turned out that water's Reynolds number is over 41,000 and a unitless number. So, hey, what was going on then with compared to air? My intuition or the intuition that I got up there was, hey, I think that water's going to be less likely to be turbulent than air, less likely to be turbulent than air, but it turns out it's more likely to be turbulent than air. And the reason is the density. Even though water is more viscous than air, in this case, given this scenario, 2 feet per second entering in and going through a 3-inch pipe, there are going to be so many molecules of water or so much mass that's trying to be squeezed in there that it's definitely going to be turbulent. Okay, let's just do one more. Let's say for some reason we've got a scenario where we actually want to make oil be turbulent. So we could either use a smaller pipe, okay, or we could use a faster speed. So I'm just going to got a number for you. Let's just say that as our last example on this, that we take oil and we really get it going, okay, almost 750 feet per second. So I'll write the number down. We're going to do oil at 749.4 feet per second, which may seem unbelievable, but there's a point to the calculation. So go ahead with oil and calculate the Reynolds number if you put oil at 749.4 feet per second through a 3-inch pipe. So perhaps a little bit of a unrealistic example, but there is a point. I got a Reynolds numbers in the 41,000, okay? And it's very, very similar to this Reynolds number right here. And in fact, the way it would be interpreted is once we get this Reynolds number, then we start working on, okay, what is the flow going to look like? So those lines are supposed to represent the side of the pipe. And the look of the flow. So for example, the degree of swirling is determined by the Reynolds number. So we would say in this case, this flow here, this water at 2 feet per second, would end up have a certain swirling nature, and the swirling nature of this oil, because it has the same Reynolds number, would be the same. All right, so the Reynolds number is telling us, hey, the likelihood of turbulence, the higher that Reynolds number is, the likelier the turbulence is, but the number itself also means something. Sometimes we use that Reynolds number, like that 41,000 that we just got, and we put it into other expressions or procedures to describe the nature of the flow. And as a consequence, you can have two different types of fluids that end up looking exactly the same. So you could have fast-moving oil end up looking exactly the same as slow-moving water. And there's all sorts of combinations that would work out that way. All right, so Reynolds was just another one of those engineers who really got into pipe flow and seeing what was going on with pipe flow. And what he noticed, what I just described, that you could have two different fluids, but if that calculation, rho v d divided by viscosity, turned out to be the same for both, the flow ended up being the same. And among the nature of the flow things he figured out was he figured out numbers for when flows had different characteristics, namely laminar or transitional. So basically, this might be a chart that you might want to put up here. Reynolds number and how we interpret the meaning of that, okay, or flow regime is sometimes a term you see in the literature. Okay, so basically what we're going to have is the Reynolds number's low, it's going to be laminar. Okay, and that is layered flow, so you have a layer of fluid and then another layer adjacent to it, and they're just flowing along. One might be going faster than the other, but they're sliding over each other like layers. Okay, if the Reynolds number's high, we're going to have turbulent, okay? And that is where we have that swirling flow, okay? In general, a line of some fluid, like an element of fluid, if that's a little particle of fluid, and this is in a pipe where the flow is going that way, that element is going to keep making its way to the right with the flow, but it's not going to be in a straight line, or it's not going to be a smooth layer. It's going to have little deviations that sometimes can be pretty significant, sometimes kind of small, but always, even though general motion to the right, deviations. Okay, it turns out there is an in-between regime of flow where we have something like layered flow, but occasionally we have little bits of turbulence, and that is called transitional. So that's going to be our intermediate. Sorry about my writing, transitional. Okay, and so all these numbers right here are for the special case of pipe flow, or the important case of pipe flow, these Reynolds numbers. So what's the low cutoff? Well, less than or equal to 2,100 is going to be laminar, or less than. Don't worry about the equals too much. We'll just call it less than. So for example, on the previous example, the engine oil, we got 111. That was definitely laminar flow. Okay, how high do you have to go to get turbulent? Well, your book has a specific number. It is a little bit different than what I'm used to for pipe flow that I see out in industry, but we're going to go with the book's number. So the book has 4,000 as the cutoff. If you get up to 4,000, you've got that turbulent type flow. I do sizing of pipe. In some cases, we want to be sure we get turbulent flow, and so sometimes we even go higher than that to be sure. Okay, and then if the Reynolds number is in between, so less than 2,100, sorry about my writing, pardon me, greater than 2,100 and less than 4,000. Okay, and I think you can see what I got there, even though my writing's a little bit messy. If the Reynolds number is between 2,100 and 4,000, we're going to get transitional. Okay, good. That allows you to do a lot of good pipe sizing, which is a valued skill out there in industry. You might think, hey, that your job is going to be to size pipe to be laminar flow, because laminar sounds good and turbulent sounds bad, and that's definitely the case if you're in an airplane. You want to have laminar flow. You don't want to have turbulent flow over the wings when you're in that plane. But for pipe, sometimes actually we do want turbulent flow. So I'll give you an example really quickly where we do. There are systems where we have a pipe and it carries hot water, okay? And we want that heat to get out of that water and get into a room. So this would be like a radiator type system. Okay, well, if you have laminar flow, the fluid that's near the edge here is close to that pipe and you actually end up getting heat coming out, okay? But this fluid that's in the middle that's 180 degrees, remember, it actually just flows in a layer like that and never actually touches the side. So the heat can only get out via conduction via layers. This fluid never makes that turn and goes down and gets close to the wall so the heat can come out. So it turns out in a case like this, we'd actually want laminar turbulent flow. So here's a good example that's a good challenge and represents something that you might do out in industry once you understand a little bit more about flow, and that's pipe sizing. So let's just I have a kind of a strange number here, but you'll see why in a bit. Let's say we're trying to size pipe to carry 44.88 GPM of water. So take an example, let's say like you're involved in a job where there's water for showers, and 20 showers, 20 divided by 44, it's a little over 2 GPM for shower, and you want that flow to be laminar. Maybe what you're trying to do is avoid noise. When flow gets turbulent and starts swirling, you hear that flow. So maybe your job is thinking, can I get this pipe big enough so that the flow is laminar? So what's the minimum diameter for laminar? Once again, given a certain volumetric flow rate, the more we spread out the pipe, the less we're trying to squeeze that water through there, and the better the flow is actually going to be. So if you want a challenge, just go ahead and pause the video and see if you can get all the way through this yourself. But once again, I'm going to break it down a little bit. First thing that I'm going to do is change the units on this volumetric flow, gallons per minute. Remember, our length unit is in feet, so we would want this to be in cubic feet per second. So that conversion, we could write it all out in detail, but we'll just reason our way through it. 44.88 gallons per minute. We're going to take that and divide it by 60, so we'll get some very, very small number, 44.88 divided by 60. And that means there's 0.748 gallons per second entering this pipe. That gives you an idea. That's a lot of flow, 3/4 of a gallon per second. But how many cubic feet are there is that, well, remember that 1 cubic foot has 7.48 gallons in it. So I could do 0.748 gallons and recognize that that is going to be 1/10 of a cubic foot. So our flow rate is going to be 0.1 cubic feet per second, and that's a volume flow rate. So you might want to pause and see, once you have that number, if you get going on it. My next step, you might want to skip, but I'm going to try to get going in it by guessing and checking. The reason I'm going to do that is my Reynolds number formula is rho v d over viscosity. And this is not a volumetric, pardon me, this is not a speed right here. That's a volumetric flow rate. And I, looking at this formula, might initially think, hey, I need to get speed. Well, my boards get a little bit messy here, but I think you can follow. We know that for flow, the volume flow rate is the volume, the speed times the cross-sectional area, okay? And so speed is going to be volume flow rate divided by cross-sectional area. So what I could do if I did guess and check, I could guess a diameter. Then once I have that diameter, I could calculate a speed. And then I could plug those two numbers in there and see how it works out. So I'm going to guess an optimistic diameter. I'm going to guess 6-inch pipe. Some of you might say that's ridiculous. I mean, 6-inch pipe is really, really large. But in some buildings, walls are relatively large, particularly dividers, say, between a shower and an adjacent area. So maybe this could actually hold a 6-inch pipe. So that's going to be my guess. I'll write that down. I'm going to just say D is equal to 6 inches and carry out the math and see, is that big enough that we end up getting laminar? So again, I encourage you to pause and see if you can work that out. So it didn't turn out very well for my 6-inch, but taking a look at the details, I got a speed of 0.5093 feet per second, so 1/2 foot per second. That's just taking the volumetric flow rate and dividing it by the cross-sectional area of my pipe. And then I can plug into my Reynolds number formula. I did density times speed times diameter divided by viscosity, 2.35 times 10 to the -5th, and my calculator punched out with 21,000. So it's definitely at 6-inch, our flow is definitely turbulent. We're going to have to go bigger to actually get this flow laminar. All right, well, how to proceed from there? You certainly might be able to reason it out given this result and be able to say in your head how much faster you need, larger you go to 6-inch. And then once you reason, check it out. But we would like to do it and get away from guess and check. So clearly what we can do is we can combine the formulas that we have on the whiteboard. This formula right here with that formula right there, and see if we can express the Reynolds number with a Q in it, okay? So just give you a precursor, and then I encourage you to try this again on your own. I am going to take this Q over A and put it in that B position, but I want there to be a D in there, so this A I'm going to express as pi D squared over 4. And so I'm going to take these two formulas and try to combine them and try to have a single Reynolds number formula that has a Q in it, because that's what we're given, and also has a D. So I encourage you to pause and see if you can get that on your own, and we'll check in with each other in just a minute. All right, checking in, here's your first step. That expression in the big brackets there, that's just the speed in terms of Q over cross-sectional area. And so there's my expression. Well, if I'm going to do more work with it, that's a mess. So it certainly can be simplified, and I encourage you to do that before we move on and actually complete the problem solving. All right, so my algebra turned out a little bit awkward, but nonetheless I believe is correct. All right, it's correct. So the q remains, and then I've got a d squared there and a d there. So one of those cancels, so I have left a d in the denominator. This 4 is in the denominator, so actually I do have a mistake there. That 4 should end up, pardon me, on the denominator. The pi, goodness. Hey, sorry, you guys. I got mixed up on that 4. So there is the correct formula. The pi ends up in the denominator, and this 4 is in the denominator of the denominator, and that ends up in the numerator. And the formula makes some sense, that given we have a certain volume flow rate, Q, the bigger Q is, the bigger the Reynolds number. And in this case, the formula reflects our intuition that the bigger the diameter, the smaller the Reynolds number would be. Okay, well, we can finish that off then. We want this to turn out to be less than 2100 if it's going to be laminar. And so now you can do the math. I would go ahead and do a little bit of algebra and isolate the diameter, and check in with me in just a second. Okay, so I took I took my relationship and wrote it and said basically, hey, here's this Reynolds number, and we want it to be less than 2100. And then I did the algebra, and I got the diameter needs to be greater than this expression. And then I'm going to fill in. And before I crunch the numbers, hey, let's take a second, worth doing, and check to see, do we get the right units for that? Right side of the equation, that expression. And I think the thing to do, once again, is to do any obvious implication and then look for a pound. We have a pound in the denominator. This is pounds second per foot squared. And we've got a slug in the numerator. And if we can see if we can combine that slug with other stuff to get a pound, then this will become much simpler. So slug per foot cubed per second. One strategy we could try is to get rid of that. Okay, so we want a foot in the numerator, and we want a second squared in the numerator. Well, this second and this second combine to give a second squared, so that's looking pretty good. How about this foot squared here? It ends up flipping up to the numerator. So I'll just go ahead and write out what we've got in the numerator. We've got a slug. That foot squared becomes a foot squared in the numerator. And then we've got a second there and a second there, and we have a second squared. And we are so close to a pound, which is a slug foot per second squared. But what I could do is I could think of this what's left in the numerator as a slug foot per second squared times a foot. And that actually is a beautiful thing, because this term right here is a pound. And it cancels with that pound there and just leaves a foot. So the units for this entire thing are a foot, which works out just great. That's exactly what we were hoping for. Works out to be a foot. Okay, so let's go ahead. We know it's going to be a foot. Let's see what kind of diameter it comes up with. Okay, so my calculator gives me 5.03. Now let's just think about what those units actually would be. And those are 5.03 feet. Wow, a 5-foot diameter pipe to avoid turbulence. But actually, that does reflect what actually happens when you work out there in industry. It's really hard to make water flow laminar. And that is because even though water has pretty good viscosity, it is so dense that we end up getting a lot of, for a certain flow rate through there, we end up getting a lot of particles going through there. And as a consequence, it's a lot more likely that it's actually going to be turbulent. Okay, so in many cases, when you size pipe for water, you're just going to live with the fact that it actually ends up being turbulent. Now, there's a way to get clearer on likelihood of turbulence, and in particular, address this sort of question, which can be challenging to our intuition. And that is if we have a certain volume flow rate, let's say like 10 GPM or 100 GPM going through a pipe, and we consider air versus water, which one is more likely to be turbulent? Well, a lot of people's intuition is the air. Viscosity prevents turbulence. Air is low viscosity. It's a lot more likely that we're going to get air jiggling around, etc., and having a sort of swirling type motion than we are water. That's our intuition. But it turns out that it's going to be the water that's more likely turbulent. And that is because the argument I just gave you a minute ago, that ignores the other part of it, and that is the question, how much fluid are we, mass essentially, are we trying to squeeze through this passage? And this is a volume flow rate, like feet cubed per second, but there's also the question of how many slugs there are per feet cubed, or how many kilograms there are per meter cubed, and that's the density. So the waters, when we compare water to air, we should consider viscosity, but we should also consider density. And that's true for any fluid. So basically, if we wrote down and said, look, we're going to think of viscosity as resistance to turbulence, well, yes, viscosity increases and turbulence becomes less likely, but also there's this whole density thing. So as density increases, turbulence becomes more likely as well. So what we can do actually, pardon me, I spoke just a minute ago, is viscosity increases, turbulence becomes less likely, but on the other hand, as density increases, turbulence becomes more likely. So what we could do is we can come up with a single factor that combines those two, and it's the ratio of the viscosity to the density. And let's just go ahead and do that calculation first for air, and then for water. And we worked in BG, or English units, of up until now. So for this example where we do the ratio of viscosity to density, let's do it in SI units. So give it a try and see, first of all, what kind of number you come up with and what kind of units you have for this new parameter that's used quite often when evaluating flow. I got a really low number, and I hope you did too. But once again, what we're saying, we're thinking, hey, this ratio for a fluid, its viscosity divided by its density, is in a sense going to be its resistance to turbulence, its turbulence resistance. If we want something to resist turbulence, we want it, in a pipe setting, we want it to be very viscous. At the same time, we want it to have low density, so that means that there's not that many particles are actually fitting through the pipe opening. And so this combination of high mu and low density will give us a huge ratio once we calculate it, and we'll show how resistant this fluid is to turbulence in a pipe setting. So when I went through it, I got this very, very small number. It's the easiest thing to do is just leave this exponent and just do that division. I got 1.455. And now the units are a little bit tough. I think it's a little bit challenging to find a kilogram meter per second squared, which is a Newton. Another alternative is just to take this big mess and write out the Newton. So the first thing I'm going to do is write it as a single fraction. Newton second per meter squared, that's the numerator, and the denominator is meters cubed per kilogram. Okay, so that's not bad. What I would encourage you to do then is take that Newton and write it as a kilogram meter per second squared, and see how it all turns out. So I'm going to erase that Newton right there, and then just write over here, write kilogram meter per second squared. That's that Newton that was there before. And then just stare at it and see what can we cancel out, and how does that end up working out. Okay, so hopefully you've done it yourself, but I'm getting the kilograms to go. That's nice. I am getting a meter squared and a meter to the fourth. So meter to the fourth, meter squared, I'm getting meter squared. And the last remaining unit is time, and I have seconds. So it is meters squared per second. And this answer right here is 1.455 times 10 to the negative fifth meters squared per second. That unit is hard to make sense of. Why is it that? But nonetheless, those are the units. Okay, so what I was hoping to do is see if we can make sense again. Why is it that water is more likely to be turbulent than air? And what we're going to do then is just do that calculation really quickly for water and see what its mu over rho is. Okay, so given what I have here, water's resistance to shear and maybe to turbulence looks pretty good. That's the viscosity. But on the other hand, it's so dense that that means for a certain flow, we have a lot of particles in there. And if you crank through it, you get 1 point, we can just round it off to this number, 1.1 times 10 to the negative 6 meters squared per second. So given this way of thinking, water's resistance to turbulence is much lower. And in fact, we can do a ratio. We can do a ratio of these two things. But one more note, if you look in your tables, you will see that there is a row that has numbers like this, okay? And if you could bear with me, I know that the camera's not working great here, but let me see if I can get that up on the screen so you can identify that. Okay. So here's our standard tables, and give it just a second to see if we can focus. Okay. Trying to get a little bit closer for you guys, sorry. Okay, if you take a look, there is I'm going to go to the next table down. There is a column next to the dynamic viscosity column that if you look down at the bottom has the same number that we just got. That's 1.12 times 10 to the negative 6. And the units are correct as well for that, and meters squared per second. So that column is mu over rho, or what's called the kinematic viscosity. And they have a symbol for it, which looks a lot like a V. It's actually a Greek letter. And let me get that up there so that we have that. Okay. We have a new relationship that we can use sometimes. Instead of using mu and rho, sometimes we can use this little, almost looks like a script V, which is equal to the dynamic viscosity, we've been calling it the viscosity so far, but it's really sometimes called the dynamic viscosity, and then divided by the density. And so if you go through and crank through that, you'll get that number in those cases. So let's take a look at the kinematic viscosity of air divided by the kinematic viscosity of water. And to get that ratio, well, you would just take this number right here and divide it by that number right there. So let me just try it myself and see if I match up with what you guys did, what you guys get. Negative fifth, so 1.455 times 10 to the negative fifth, that's air, and then divide it by 1.12 10 to the negative sixth, and I get a very, very large number. Let me just confirm that, and I'll get it up there for you guys. Yeah, so I got that ratio to be nearly 13. My calculator is 12.99. So a fairly good way of interpreting this, what this is telling us is that air is 13 times as resistant to turbulence in a pipe flow regime situation than water is. And once again, the culprit is the water's density. And it'd be interesting if you take a look through that table, you're going to see that engine oil, which is even fairly close to the density of water, its viscosity is so huge that its kinematic viscosity is really large compared to water and air. So engine oil is kind of a champion in that regard. Summing it up then, we have a pipe flow situation, and we want to do some engineering and figure out what's going to happen in that situation. As far as the nature of the flow in the pipe, what we're going to do is we're going to calculate the Reynolds number, and we can do it by doing the density times the speed times the diameter divided by the viscosity, and that is our basic equation. We might have situations like this where we don't actually have the speed given, but of course we can use the other relationships we have to work that out. And then in addition, you can see that we could take this density and move it into the denominator, and I'll just quickly write it down below and then summarize it. Then the expression for the Reynolds number would be rho V, instead of rho VD over viscosity, I'm going to erase that density, okay, and it's going to go down here in the denominator, and this term right here is the kinematic viscosity. So another way we can work it out, going back to our summary, is we can do VD divided by the kinematic viscosity. And that can be a shortcut at a lot of times, that helps us figuring out what's going on. Then, given two flows that sound very, very different, like maybe one's engine oil and maybe one's air, different diameters, different volumetric flow rates. If the Reynolds number turns out the same, the nature of the flow, the degree to which it's turbulence, and some other factors involved in it are going to be identical. So this is a very fundamental and helpful calculation. So to finish things off for today, one last parameter from chapter 7. So again, one focus in chapter 7 is taking a bunch of different factors like density, viscosity, temperature, etc., and doing a calculation with them to come up with a parameter, and that tells us something about the flow. So one more interesting one, again, the Reynolds number is the main one. It's called the Mach number. And with the Mach number, what we do is we compare the speed relative to the fluid of some object. Again, we're talking about the interaction of an object with the fluid. So my crude picture is supposed to be an airplane flying through air. So there's some air there. And it's going at a certain speed, 400 miles per hour, 500 miles per hour, etc. To the compression travel speed, the speed with which a compression would travel. And you can see that might be important. Maybe just putting some numbers up there. Let me just put a 400 up there to say this plane is going 400 miles per hour. Well, what its tip right there, or any forward surface of it, is going to compress the air as it hits against it. Well, that compression travels, okay? That compression travels. And ordinarily, like for you and me, when we walk down the street, this compression that we create travels much, much faster than we do. So we don't have the problem of a compression just staying right in front of us. But what if this compression does not travel much faster? Well, then you have this compressed area that builds up here in front of the plane, and that can make a huge difference. So one calculation that you would do for planes that fly at significant speeds, or other objects as well, is compare the speed of the object relative to the fluid to the compression travel speed for that fluid. And that is called the Mach number. In symbols, we calculate the Mach number by doing that comparison. We take the speed of our object relative to the fluid. So if this object was going 500 miles per hour and the air was still, this number over here would be 500. If this was still and the air was coming this way 500 miles per hour, once again, we would put 500 miles there, divided by C, where this represents the compression travel speed. And sound basically is a compression, so the compression travel speed is actually the speed of sound. So to get the Mach number for some sort of object moving through a fluid, we take the object speed and divide it by the speed of sound in the fluid. And information that allows us to do that calculation is in many standard texts, and of course it's all over in the text. In particular, if you get to the chapter on high-speed flow, I just want to finish off this lecture by doing one quick example with that and see how that turns out. So let's just take a case where this plane's going pretty fast, okay? We're going to have it going 800 miles per hour, okay? 800 miles per hour. Now, the compression speed depends on all sorts of factors, including the air temperature and some other factors as well. Also, how high we are in the atmosphere, et cetera. I'm going to use a rough number, so 1125 feet per second. Okay? And you may find some different numbers in the book depending on situations, but that's a good rough number to use. Okay, so I would encourage you to pause and see if you can come up with the Mach number, see if you agree with the numbers that I got and the units. So go. All right, well, my math turned out to get Mach 1.04. I took that 800 miles per hour and converted it to feet per second, so it's 1173 feet per second. And then I did 1173 divided by 1125, that would be the speed of the compression. And I get this plane is going a little bit faster than the compression, and that is a huge deal for air flight. It works out to be 1.04. Units, well, hey, it's a unitless parameter, and all those parameters in chapter 7 are unitless. What do we do with that? Well, first of all, once then we know that the Mach number is 1.04, it's kind of like laminar versus turbulent. You know that this plane is going faster than the speed of sound. We're in supersonic flow. This pressure is really going to build up here, and as a consequence, we'll get a sonic boom. And there are some other calculations related to the flow that we can work out based on this Mach number. Additional note, is this just for air? No, it's for any sort of fluid. So if we had a torpedo going through water and we worked it out and we got its Mach number was greater than 1, yes, once again, we would have supersonic flow. And if the Mach number of the torpedo was 1.04, the flow here and the flow of the torpedo would bear some important similarities that are revealed by the Mach number. Okay, well, that's a good start on chapter 7. And in addition, we're actually venturing into chapter 8, because chapter 8 is about pipe flow, and the fundamental first calculation you do is Reynolds number. You'll be getting more information from me via email. Please let me know if you have any questions, and keep working towards getting number 7 done. My next task is going to be get number 8 ready for you guys. Have a good evening.